Hi group, it's Mrs. Schaus, ready to talk to you about section 1.12, which is on writing variation equations. We are going to find constants of variation, write equations for various types of variation, direct and inverse, as well as joint and combined, and we will use those models to solve real problems. Okay, down below here, in the second portion of the page, I put down the type of variation and the general model. So in each of these models, the K is representing the constant. Sometimes we call that the constant of variation, like we had said up above right here, find the constant of variation. Sometimes that's also called the constant of proportionality. Okay, direct variation says that y equals the constant times x, or x raised to some power. They call that direct variation. Inverse variation, y equals k divided by x, and again it could be to some power. Really, it could even be a fractional power, so you might see a root. Joint variation means directly varying with more than one variable or variable to a power. And combined means you've got some joint relationship and inverse relationship. So here, y would be varying directly with x to whatever power and inversely with z to some power. So you won't in the problem hear the word combined variation really used. It'll say y varies directly with something and inversely with something else. But you could hear the term joint varying jointly within the problem, because it could say y varies jointly with x and z. Okay? All right, so using those sort of general models, we want to be able to do a few things. We, again, want to be able to find our constant of variation, and we want to be able to write a variety of models. So let's take a look at some problems together here. First of all, write an equation for the situation. This tells us that L varies directly with X. So again, I go to my model that says direct variation, and it tells me that L would equal some constant times X. Do I know what this constant is in this case? No, I don't. This would just be a general model, but you'll see in some of the upcoming problems that we will be able to find the constant of variation and write a specific model for that scenario. For the next one, it says R varies inversely with the square root of P. So again, inverse variation means R equals K divided by, and then whatever variable. Well, again, the power on the variable, in this case the variable is P, doesn't have to be a whole numbered value. This says the square root of P. So I could write that as the 1/2 power right here, or I could actually use the square root symbol. Either way, R varies inversely because of the division, K divided by the square root of P. All right, in the next problem, they're going to ask us to find the constant of variation, write the model, and then use the model to answer the question. All right, so we start by reading A varies directly with B and inversely with C. That means the model would be A equals K times B, since it's directly with B, but divided by C, again, because of the inverse relationship there. Here is our sort of general model where we don't know the value of K, but when we read on, they give us an ordered triplet. The value of A is 1, when B is 2, and C is 10. So they give us numbers, numeric values to plug in for A, B, and C that will allow us to solve for that constant. Let's see what we get when we do that. And to solve for the constant, I'm solving this like an equation here. That's what it is, right? Multiply by 10 on each side. These cancel, and I get 10 equals K times 2, or 2K, right? Divide by 2 on each side, and we get 5 is the value of that constant of variation. So now I could go back up here, and I could rewrite the model, but using my specific K value. So there is our specific model for this situation, and I could be given any of these two variables to find the third. They are asking us to find A when B is 7 and C is 9. But they could have asked me to find a different variable as well, depending on, what was needed. All right, so just got a little bit of cleanup to do here. 5 times 7 is 35, divided by 9. I could leave it as 35/9, or I could approximate it either way. Box that answer in. That's a great answer. If I want to do 35 divided by 9, I get 3.8 repeating. Okay, moving onward. Here's another similar problem. Find the constant of variation, write a model for the situation, and then use the model to answer the question. We're told that m varies as the square of t and m. So, I'm sorry, m varies inversely as the square of t. And then the latter part is when m is 10, the t value is 2. We'll use that to find k in a moment. All right, so I've got an inverse variation problem. That's k divided by, and then the square of t would give me t to the second power. So again, there's my sort of general model. I'm going to plug in the ordered pair that was given, 10 for m and 2 for the t value, and I'll solve for k. Remember, this is really 4 when I do the squaring here, so I'm going to multiply by 4 on each side. This will cancel, and I get 40 equals k. Okay, so I can use that k value to plug into my model. M equals 40 over t squared. And like I was saying before, now we can use that model. If we know any value of m, we can find t, or any value of t, we can find m. We're asked to find m when t is 4. All right, since we've got a square here, that really gives me 16. And I can reduce that down a bit. Let's see, 8 goes in here 5 times and in here twice, so 5 halves. I like that answer. I could write m equals 5 halves and leave it like that, or m equals 2.5, 2.5. Either one is fine. All right, let's take a look at some applications. I mean, after all, this is the whole reason for making sense of variation problems, is so that we can apply them in real context. Kelly decides to empty her pool for the winter. She knows the time t required to empty the pool varies inversely as the rate r of pumping. Write an equation that models the situation. So if you get kind of bogged down in the wording, look for the specific information that you need. That is, the time t varies inversely with the rate r. So since it's an inverse relationship, I'm going to write t equals k over r. And there is my, again, general model. In order to be able to use this to answer some real problem, I do need to determine what the k value is. So as we read on the next part, you'll notice that they give me an ordered pair. Last year, Kelly was able to empty her pool in 45 minutes at a rate of 800 liters per minute. She now owns a pump that can empty the pool at a rate of 1 kiloliter per minute. How long will it take to empty the pool with the new pump? All right, so we're using this ordered pair, 45 minutes and 800 liters per minute, to plug in and find the k value. The time, 45. The rate, 800. And it is important here, if they had given me 3/4 of an hour and this is liters per minute, I would have had to change that 3/4 of an hour, 2 minutes. So make sure that your units, oops, sorry about the light there. Make sure that your units kind of make sense within the context of the problem. All right, so now if I multiply by 800 on each side, that will give me the constant that I'm looking for. 45 times 800 is 36,000. So now I can write the model. Time equals 36,000 divided by r, the rate. And since I have that model now, I'd be able to plug in any time to find the rate at which the water was being pumped. Or if I know the rate, I would be able to determine the time that it would take to empty the pool. All right, so the question is, with this new pump that is pumping at a rate of 1 kiloliter per minute, oh, that's the same thing as 1,000 liters per minute. So again, staying consistent with our units, I'll need to use 1,000. Time then would equal 36,000 divided by 1,000, which would mean my total time would be 36. And again, being consistent with my units, this was liters per minute, this would be 36 minutes. And in the context of the problem, that, you should kind of stop and ask yourself, does that make sense? Well, yeah, it took 45 minutes for a pump that was pumping fewer liters per minute. So now if we're pumping that a little bit faster, it will take less time to empty the pool. All right, one more application, and then we'll let you try some on your own. All right, in this application, it says a lumber company needs to estimate the volume of wood a load of lumber will produce. They know the volume of wood in a tree varies jointly as the height h and the square of the tree's girth g. All right, before we continue on with the reading, let's think about writing our general model. Again, go back and kind of extract out the pieces that you need. They know that volume varies jointly as the height h, and be careful, don't just say girth g, this says and the square of the tree's girth g. I hope you guys know that girth means like the thickness, right? If you were to hug the tree, that would kind of represent its girth, right? All the way around the tree, how thick that it is. Okay, so jointly, remember, means directly with more than one variable. So I'm going to write V, the volume, equals K times H, the height, and again, be careful, the square of the girth G. So I'm going to write G squared. All right, so now at this point, I want to find my K value so that I can use it to answer other questions. They observed that a tree 40 meters tall, so that's the height. I'm going to put that in place of H. Girth is 1.5 meters, and it produces 288 cubic meters of wood. So I'm actually going to put in that 288 for V as well. What was that height again? It was 40 meters tall. And the girth again, 1.5, and that's going to get squared. So I'm still solving for my constant by isolating it. I've got some work to do here. I'm going to take my calculator and do 1.5 squared and then multiply that by 40. I get 90. So now I'm just going to take the 288 and divide by 90. Divide by 90 on both sides. And I get that K equals 3.2. All right, so when it asked me to write a model for the situation, they're not just talking about this general one. They wanted us to find the constant and go ahead and plug that in. So volume equals 3.2 times the height times the girth squared. All right, with that model, again, if they give me volume and height, I could find girth. If they gave me girth and height, I can find volume. If they give me any two, I can find the third one. The question here is what volume of wood, well, that does seem like what we would be most concerned about, is how much wood can I generate if this is my business, right? What volume of wood can they expect to get from 50 trees averaging 75 meters in height and 2 meters in girth? Now, keep in mind that the number of trees wasn't considered in this problem. This is the volume of wood produced by a tree. But if these trees, on average, have the same height, or a height of 75 meters and a girth of 2 meters, I can plug that in and find the volume of one tree. So I'm going to call that V sub 1. V sub 1 equals 3.2 times a height of 75 meters and a girth of 2 meters. And we're going to square that. So let's see what we got. 2 squared is 4. Multiply that by 75 times 3.2 and I get 960. All right, so if that is the volume for one tree, and we have 50 trees, then V sub 50 is going to equal 960 times 50. So if I multiply by 50, I get 48,000. 48,000 what? Let's see. It is volume, so we know it's going to be a cubed unit, and we are working in meters, so this should be meters cubed. Okay, folks, I'm going to end the video in just a moment here, and you'll have the opportunity to try some exercises and get some help in class the next time I see you. I hope it's a great day, folks. Talk to you soon.